Fantastic. All right. Yeah. So thank you very much for inviting me. Thank you very much for running this summer school and the project, and also thank you for the kind introduction. My talk today is about bias and fairness in machine learning. And when I got this invitation from Steffen, I was thinking, I also want to talk a bit about my own research, of course, because that's where I'm, an expert in. That's where I know the most about. And so my lecture today will try to build a bridge between bias and fairness in machine learning and our recent work on using, machine learning and explainable AI technologies to, work in the medical domain. And so my presentation consists essentially of two parts. And the first part being more on, kind of what is fairness in machine learning? How do we actually make decisions there, and what should we be aware of? And what type of work has been done in the area of fairness in machine learning on a high level, and then to build this bridge and use this as a bridge towards my own research. Before I start, however, I wanted to very briefly talk about the company that I'm currently working for. So it's called NEC Laboratories Europe. NEC is a Japanese IT company, which is located mainly in Tokyo. So they have, it's a pretty big presence in Asia. So they have several skyscrapers in the city there that you see on the top picture. And then about 25 years ago, NEC decided they also wanted to open a research lab in Europe, and decided on Heidelberg, Germany as the location, and that's where I'm currently at. At the moment, we have about 90 researchers, lots of different nationalities, so we are quite diverse. And our main objectives are essentially working on basic top-tier research, and we are not actually involved directly in product development, but of course, the type of work that we do is typically transferred over and used in some form or shape also in products. And I can say that for NEC as a company, ethical, trustworthy, fairness, machine learning or fair machine learning are also getting increasingly important. Also because NEC is quite active, for instance, in the medical domain, and I'll touch on this a bit in a second. And in the biomedical domain, where clearly, when you design machine learning methods that potentially impact, for instance, patients and their well-being, you also have to be extremely aware of the possible, harmful consequences of using machine learning that is biased. And so I think, the topic of this project that you're running and this summer school is also very timely and very interesting also for companies, for IT companies. The research, so in NEC Laboratories Europe, we have several different groups. The group that I'm currently, leading is the machine learning group, and we are essentially working on two major themes. One is graph-based and geometric deep learning, which is essentially about applying and developing deep learning methods for, data that's not, images and text, essentially. Also specifically knowledge graph-based AI. And the second area of our work is in explainable AI, where we're specifically interested in combining, deep learning and reasoning, kind of discrete reasoning capabilities in machine learning methods to quantify prediction uncertainties, which is also something that I'll touch on later when it comes to, fairness in machine learning, and also increasingly human-centric AI. So, looking at AI systems as a system that combines, and has humans and machine learning methods interact, and to study that as a single system. I should also say that, typically I'm very happy about questions. Since I'm not very familiar with the WebEx system, I don't think I can see any questions. So yeah, let me know if asking questions is okay, and then also, if it's okay, how I would be able to see that there is a question. Yeah, not sure how this works.
We'll let you know if somebody has a question. Mac and I will keep an eye on it. We'll let you know so you can concentrate on sharing what you want to share.
Okay, sounds great. Yeah, and please ask questions now that I know that you can. Please ask. Yeah, so my talk is roughly dividable into 4 parts. So the first one is fairness in statistical decision making. My understanding of the audience here is that it's pretty heterogeneous. So some people might be very familiar with machine learning, AI technologies. Others might be maybe more in the area of law, social sciences. So I'm going to kind of start my presentation by talking very high level about fairness in statistical decision making. What are the the pitfalls but also what are the opportunities there from a point of view of me as a more technical machine learning researcher. Then I'll also discuss a bit concepts of fairness in machine learning that have already been developed and formalized. And then finally, I will kind of go over into more specific research topic of my group, which is explaining the behavior of machine learning methods, which then of course can also be used to potentially reduce unfair behavior of machine learning methods and biased behavior of machine learning methods. Okay, so I should also say that there is a fantastic book actually in the making on fairness and machine learning. So it's really a very active research area. It touches on many different concepts like graphical models, for instance, probabilistic graphical models, which is a research area that I'm very familiar with, but also causality, causal reasoning, and it's a very big and interesting research area. And if you're interested to learn more about this, if you don't already know about this, then I can only recommend this Fairness and Machine Learning book by Barokas, Hart, and Narayanan, which is freely available on the website that you see down here. All right, let's get started. Yeah, as many of you probably know much better than I do. Decisions made by others have a huge impact on our life, much more than we might think sometimes. So just to give a couple of examples, right? If we are applying to schools, to universities, if we are being promoted or evaluated within our companies or universities, if we want to apply for a loan from a bank, or if we actually get a diagnosis, in each of those cases and potential treatment plan, right? In each of those cases, we are relying on others, at least partially, making decisions for us, and this has a huge impact on our lives, right? And of course, for the obvious reasons, we want decisions to be made, in, I'm putting this here quote unquote, the right way and for the right reasons. And of course, later on, we'll unpack these kind of fluffy definitions a bit more. But generally, I think we could agree on 3 kind of, properties that we want decisions, the way the decisions are made, to have. So we want them to be consistent across individuals and groups. We want them to be relevant to the outcome of interest. So we don't want, for instance, particular attributes of ourselves be included in a decision about a bank loan that we don't see as relevant. For instance, the types of friends that we have, or how tall we are, right? It's pretty obvious. And finally, and this is obviously the focus of this presentation, we want the decisions to be fair and unbiased. So we want, again, a decision to be made in a way that it doesn't disadvantage in an unfair way, for instance, particular subgroups of a population. And here just a little caveat, instead of using the term bias quite a bit, I know the project is called NoBIAS. I prefer to actually refer to it as fair or fairness in machine learning, because bias has a particular different meaning in machine learning, and so I try to avoid it, so just to make sure that it's clear what type of bias I'm talking about. So right, there is a lot of criticism, a lot of scrutiny on nowadays on on AI and machine learning and how it could actually impact decision making, and I think that's really good that it's the case. But of course, we shouldn't forget that decision making as it is done now by humans mainly is also not necessarily unbiased and fair. Oftentimes, decisions about other humans are made kind of based on intuition or past experiences or what I would call a gut feeling. So for instance, when you create performance evaluations in companies, right, or when you hire people into positions in companies, which is something that I do, you are also following, to a certain extent at least, right, also your intuition. And so you might actually fall prey to certain biases that you are actually not actively aware of, right? And we'll talk about this actually quite a bit. Human decision making is extremely biased in many cases, right? And so the idea is that while we should also, of course, pay really close attention to the pitfalls of statistical decision making, of data-driven decision making, it also provides, I think, a lot of advantages or lots of opportunities, at least, right? So one thing that I always find extremely important is that it forces formalization. So instead of because we need to use algorithms, we need to use a mathematical framework typically for data-driven statistical models. It forces us to define well, what are the features that we are looking at? What is the target variable that we want to predict for, that we want to make a decision about, right? And by forcing us to formalize the problem, it also might, unearth essentially particular biases and difficulties and problems that might be inherent in existing human decision processes, right? And it also makes it easier to communicate to others, how we are actually making decisions. So for instance, if I would ask a manager in a company, so how do you actually decide whom to hire? You would get probably a very different answer depending on who you ask, right? And it would be also not very crisp and clear how it is done. Oftentimes relying again on intuition and gut feeling. And then of course we want to also use the data that's available increasingly, right? So many decisions and the input to these decisions is nowadays recorded. And so we have a lot of historical data available to us that can allow us to actually analyze the data and potentially come to, statistical methods that are actually less biased than the decision making that humans are partaking in. And so one example that I kind of like, which is also a bit, maybe a bit more lighthearted than other examples, is this book by Michael Lewis about the baseball team, the Oakland Athletics, which is a baseball team in 2002 was a baseball team with a very small budget, but because they decided to hire someone who can do a more rigorous statistical analysis of player performance and the types of metrics that are used to evaluate player performance, they could actually outcompete other teams that would, even though they had a much higher budget, rely mainly on scouts and their gut feeling and their intuition, right? And so this is kind of showing, or maybe symbolizing the let's say the promise or the opportunity of statistical data-driven decision making, is that you can do much better than what maybe you have done traditionally by just relying on some sort of inherent human expertise and intuition. And so, I spoke about kind of statistical decision making in kind of a broader context. And now, as I said, I'm an expert in machine learning, and what machine learning is very good at is to discover, factors from historical data that are really relevant to the decision. So I mentioned this as one of the things that we want decision making to be like, right? We want the decisions to be made in a way that they're relevant to the target at hand, to the problem at hand. And I think that is something that machine learning can bring to the table. And also now, especially for data like images and text and these types of data sources, machine learning is also able to discover statistical patterns that humans might not even be able to articulate, right? And so it also allows us to use these very, kind of complex but very successful, neural network-based machine learning methods, for instance, to make predictions much more accurately than if you would use a simpler model, right? But of course, so this is kind of the opportunity again that machine learning can bring to the table, right? And there have been a lot of successes here. But of course, the problem is that the quality of the decision making, of the machine learning based decision making, hinges on the quality of the data and the statistical model, right? So just because machine learning learns from data and is therefore evidence based, does not mean it is automatically generalizable, reliable, and fair. And here are three examples at the bottom of this slide that kind of address these three concepts of generalizable, reliable, and fair, and which have been, I think maybe many of you have seen before. So for instance, what machine learning methods are pretty prone to is to latch on to what's called spurious features, right? So for instance, in the case on the left here, the goal was to train a machine learning model to distinguish dogs, from huskies, essentially, or other types of dogs from huskies, German shepherds from huskies, or something like this. And it turns out that this model worked really well, but it turned out that it actually was, when you kind of analyze where is the model actually intuitively looking at, right? It turns out that it was actually using the snow in the background to make this classification decision, right? And of course that's bad, because you want the features and the attributes that these models take into account not to be something about the background, because you also want to recognize a husky or distinguish a husky from other types of dogs when it's not standing in front of a patch of snow, right? And this is a pretty benign example, right? But there are other examples, for instance, from medical imaging, where doctors would put the radiologist, for instance, would put a little mark on the X-ray scan, right? Machine learning would turn out to work extremely well, but when you look closely, you realize that the machine learning method has actually detected this particular mark of the radiologist on the X-rays and didn't actually pay attention at all to the X-ray itself, right? So you can see that here again, these so-called spurious features lead to a lack of generalizability of your prediction performance. Then also, and I'm sure this, most of you have seen this before, machine learning is also not quite robust in many cases. So, for instance, here you want to maybe classify, animals, 100 different types of animals into their respective species. And here, you have a pretty high confidence for panda. But if you introduce a little bit of noise, so small that for us, to our eyes, the picture on the right looks exactly the same, right? But suddenly the model is now classifying it as a gibbon, right, with a very high confidence. And so this shows that these very kind of complex machine learning models are also relatively easy to manipulate and to attack, so to speak. And then finally, there's also oftentimes a lot of bias in the machine learning, in the prediction models based on machine learning. And so there's this example, about kind of granting essentially bail, or deciding whether some person that's in custody should be released on bail. And a machine learning model that was actually in use, was trained on historical data. And it turns out when people analyzed this, that there was a very strong racial bias here. So that if the person was, for instance, African American, that for the same record, for the same kind of past offenses in their criminal record, the probability that the algorithm suggested no bail was much higher for African Americans. And so it shows that because oftentimes these machine learning models are based on past historical data, and because sometimes they even amplify biases in the existing data that we have to be very careful when we use these methods in practice, because they can lead to kind of vicious cycles and amplifying actually biases. So then let's kind of look a bit more, conceptually at a typical machine learning loop in the wild, and where things can actually go wrong, right? So here, we have, let me actually change this to a highlighter. Oh, no, it's the wrong one. It's a pointer. So here, this kind of, the flowchart diagram that you see here kind of depicts essentially a typical situation when you apply, machine learning to some real-world problem, decision problem. So you have the state of the world, right? You take measurements from the state of the world, which results in a particular data set. Then you use the data set to learn a statistical model, like a machine learning model. And then you use that machine learning model to take a particular, potentially set of actions, which then influences potentially also the behavior of the individuals and the populations that this model is working with. And so we also have this feedback loop, right? Because the behavior, so our actions that we take, might actually have might actually cause the groups and individuals to actually change their behavior. And so a lot of things there can go wrong. So first of all, the problems with measurements and data are pretty widespread. So measuring statistics, and especially, and again, I'm sure that many of you who have more of a background in the social sciences and in other fields, you know this much better than I do. So measuring statistics, and specifically statistics about people and society, is not as straightforward as it might seem to a naive machine learning practitioner. So just to give an example that I also found in this book. One of the things, that was a kind of a project of the New York Times, and they wanted to track demographic diversity on college campuses in the US over 35 years. And there was a survey on racial background, as is typical in the US. And then after about, I think, 15 years or so, a new category was introduced into the survey, which was the multiracial category. And as you can imagine, right, when you introduce a new category into a survey, while you're still collecting data, this of course changes completely the distribution of who, of the existing, racial categories. And so it changes completely what people answer here, and kind of shows that even for a seemingly simple problem like tracking diversity on college campuses, this is a non-trivial issue. And also, as again, many of you know better than I do, I think race, this is the consensus nowadays, that race is really a social construct, right? Whose perception and definition changes over time. So, what is Caucasian? I mean, I'm German, but I lived in the US for 8 years, so I also was asked to fill in these surveys at some point, and I was surprised that I was considered a Caucasian, and I was wondering, what is that actually? How is this defined? And so this is also already a big challenge, is that especially when you talk about populations, about when you make decisions about people, these types of attributes that you might want to use, like attributes like race, right, that you might want to use or not use in a machine learning method, they are very difficult to really crisply define. And that's something that is, I think, also really important for machine learning practitioners to know, is that you don't even have to train a model to introduce necessarily biases in decision making. It can already be the way that you actually conceptualize and define the problem. Like, for instance, how do you define the target variable that you're interested in? Let's say you want to build a machine learning system that helps to evaluate employees in a company, right? So before you even start training the machine learning model, you have to decide, what does it mean for someone to be a high performer, right? And by defining this particular target variable in a particular way, you're already introducing particular view of yourself of what a high performer is. You're already introducing a particular type of bias. And again, this is before you even start to collect data and train the model, right? And I think this is really crucial also for machine learning practitioners who are collaborating in these types of projects to understand is that there are many different areas where bias can kind of creep into the overall decision-making system that you're constructing there. And then finally, we also use oftentimes, instead of using something that we actually care about, like crime, for instance, right? So we want to maybe predict crime in a neighborhood, but we might not have the data for that. So we use something else as a proxy, right? For instance, arrests. And you can imagine that also causes a lot of potential for harmful consequences of then deploying such a system. So I mentioned that, even before you actually train a statistical model, there's already a danger to introduce biases and bad biases, essentially, right? Unfair behavior. But then, of course, this is also true for the statistical models, the machine learning models themselves. So as I said before, right, machine learning models are extremely good at picking up patterns in data, even if these patterns are quite subtle or not obvious to the human eye, right? And so in the way that they pick up patterns extremely well, they also pick up undesirable patterns really well. Like, for instance, stereotypes and biases that are already inherent in the data on which these models are trained. So for instance, this is an example from Google Translate, which made the headlines, I think it was probably a year or 2 years ago, where, so just as an example, so Turkish is a gender neutral language. So, there is no he, she, it, there is just O. And so when you used Google Translate to translate something like she is a doctor, and you translate it into this gender neutral language and then translate it back, it comes out as he is a doctor. And if you translate in the same way and back translate he is a nurse, it comes out as she is a nurse. And the reason why this is happening or was happening is because these machine translation systems are based on machine learning and are trained on very large data sets. And these data sets already have a bias that, doctors are typically male and nurses are typically female, right? And so again, if we want to mitigate biases, we also need to understand, how these models work and what type of biases they might amplify. And so I think it was, as I said, it was about a year ago. Now Google, when you type in, the Turkish kind of gender neutral sentence, it suggests both the female and the male version, right? To kind of, again, the idea is that this helps to mitigate biases in society and in the data. So that's the first thing. The second thing is that obviously, and this is, kind of true generally, not much is really generally true about machine learning, but this is, I think, pretty generally true. The more data you have, the more high quality data you have, the better machine learning works. And obviously, if you are now talking about minorities, for instance, subpopulations, and typically you collect less data about them. The studies are typically not run in the same way that they're run for other types of, for the majority population. And so while, machine learning methods might work on average really well for a population of a country, it might turn out that they work really poorly if you apply them specifically, or if you look specifically at the performance of these machine learning methods on a particular subpopulations and minorities. And I mentioned this before with my kind of more lighthearted example with the husky, with the gibbon and the panda. Also manipulation is possible. So these models are oftentimes quite brittle, not super robust. Some adversary could actually try to manipulate also the way that these models work by, for instance, changing the data or changing, if there is access to the model, also changing the parameters of the model, these types of things. So which is called adversarial attacks. And then finally, there is also a problem with the feedback loop and data drift. Clearly, and this is especially true for populations and societies, right? The characteristics of them shift over time. So, kind of what you see on the right here is kind of the change in party affiliation, voting patterns in the United States over a certain time span, and you can see that there is a large. So red means more Republican, blue means more Democrat, and you can see that in a short amount of time, you actually see a lot of kind of shifting behavior there. And if you train your machine learning model in one time step, and then you just keep that and you continue to use it into the future, that of course causes a lot of problems. Also, when you actually get feedback from users, so the typical example is if you're Google and you want to evaluate how well your ranking algorithm actually works, it's oftentimes not quite clear how to interpret the user feedback. So for instance, if you show a user, the top 10 based on a keyword search, 10 web pages in the ranked list, and the user clicks on the first result, right? You don't know if that's because it was actually the best suggestion for the search term, or if it was because it was ranked number 1, right? And the user just kind of always clicks on the first result. And so it's already difficult to interpret in many cases what was actually the intention of the user when when they performed a particular feedback action. And then of course that's also pretty obvious, I think, is that the predictions that we make and then the actions that we take potentially based on the predictions are actually changing also the data on which we then actually train the models, right? So one example is, for instance, policing changes, right? If we have, and which can also then create vicious cycles, feedback cycles, right? You detect using your model that there is a lot of, there are lots of arrests in a particular neighborhood. You send more, you increase policing in that particular neighborhood. If you increase policing in a neighborhood, automatically the number of arrests go up, even for maybe minor offenses. And so you're creating also these feedback loops that are actually amplified using statistical decision making. And then, of course, not just in the short term, but also in the long term, your predictions might change the entire behavior of a population, because now, based on the arrest and crime statistics that you collected, people might decide not to move into certain neighborhoods anymore, and so forth, right? So you have definitely this danger of introducing feedback loops and making a problem worse. Now, this sounds all pretty daunting, right? So lots of things lots of places where something can go wrong. But in spite of all of these risks, that I just outlined, I still think that machine learning and statistical modeling in general can have a net positive impact, I think, on at least in some of the areas. So I mentioned this before, and again, I wanted to also provide a more positive outlook to the next part of my my presentation. Human decision making is already biased. I mentioned this before, and statistical methods could be used to explore and mitigate these biases, right? We don't necessarily might want to use statistical methods to actually make the decisions for us, right? But we might actually want to use statistical methods to analyze how decisions are made at the moment and to see if maybe there's a problem there. And I mentioned this also before, that by using algorithmic and mathematical approaches to decision making, it forces us to formally define and discuss and communicate how we conceptualize, formalize essentially the decision making problem, ranging from the attributes that we use and how we define them, to the target variable and how we define it, to the particular type of machine learning method and the actions that we take and how we take them based on the predictions of the machine learning model. All of this is made, invisible, or more visible maybe than it is in human decision making, right? And yeah, in general, I would say that using and kind of applying and developing machine learning methods for decision making avoids or makes it more difficult to avoid the hard questions surrounding the concept of fairness, right? For the reasons that I mentioned. All right, so this was kind of more like a high level, right? A high level view of you know, where I personally see and where many people see the dangers of you know, the potential harmful ways that, yeah, using machine learning and statistical methods for decision making can bring. Now I want to introduce, and again, my assumption was here that not every one of you knows exactly what supervised machine learning is, what classification is in machine learning. So I also wanted to you know, briefly give you some basics here. You know, so typically in machine learning we assume that there is some training data, and it typically comes as a set of pairs where each xi is an instance. So you can think of that, for instance, as you know, a set of attribute values that exist for each of the, you know, for each of the members of a population. For instance, employees of a company, like age, you know, how long they've been in the company, how many projects they successfully finished, these types of things. Then we have a target value y, which is something like, you know, for instance, in our case, we might want to be interested in evaluating the performance, predicting the performance of an employee. So this might be, you know, some sort of categorization of performance measures. And then we assume that these pairs, so consisting of the instances and the labels, are sampled from some underlying distribution. And the distribution, of course, we don't know, right? So this is exactly what is uncertain to us, what is unknown to us. And then we typically in machine learning, we choose a class of possible learners, which are here called hypotheses. And each is essentially a function, right, that takes the instance as input and outputs a particular prediction, right? So here you can see it better because this is with random variables, this is with particular inputs. So we take a particular input and we make a function returns an output y hat, and that's our prediction for the target value, right? And then we can define what's called a loss function. It kind of measures the difference between what our classifier predicts and what the true outcome is. And then we essentially during training we change the parameters, so the way that, you know, we can influence the behavior of the classifier in a way such that the loss function is minimized, right? So that it oftentimes, or in as many cases as possible on the training data, makes the right prediction. And in the rest of my presentation, I also oftentimes use y as the target variable. So you can think of that as a random variable, x as the distribution over attributes, and our y hat is the is our prediction essentially, right? Our classifier. And just to give you an example here, you know, this is a very simple example where our instances are consist of essentially they have two features. So you can think of the, you know, the x and the y axis as each being a particular feature, because we have, you know, we are in the plane here. So every instance is essentially a dot in this plane. Our target variable is either -1 or +1. So this is a binary, you know, classification problem. Something like, you know, the person should get probation or the person should not get probation. And and then you can, and this is also kind of, you know, visualized here with the colors on the right. And then you can come up with a particular class of classification methods. And in this case, it's just a line, right? So you have a line that you learn, and you learn it in a way, so it's kind of a decision boundary, right? You learn it in a way that it, as well as possible, separates your instances with a label or target attribute -1 and +1, right? So that's kind of supervised machine learning 101. And again, just to put this into the context of what I said before, so, you know, for the, you know, the Husky example, we would maybe also have, you know, binary classification problem like is Husky or is not Husky. Here we would actually have more target variables because it's probably a classification problem where we're not just looking at panda and gibbon, but also other types of animals. So our yi would not just be drawn from 2 values, but maybe, you know, how many animals we want to distinguish, maybe 20, 100. And then here also the yi would be again binary, because we are making a decision, you know, parole or no parole, right? Very quick detour, since I'm explaining, you know, machine learning methods. So, you know, I mentioned before that bias is also used in a different context in machine learning. And essentially, the idea of bias is that, you know, when you actually have a data set, and you can think of in this column, in this row here of regression, and this one in classification, these are things where you want to fit essentially a curve to these data points. And you know, on the left here, you fit a very simple function to this data curve, and this has high bias, right? Because if you look at your data, there is oftentimes a pretty high distance from the data point to the curve that you fit here. Whereas in the middle here, you have, you know, much lower bias than on the left, because, you know, when you again look at the distances of the points to the curve that you're fitting here, it's much closer. And then on the right side, you have even lower bias, because you're almost going, you know, through each of these data points. And this is the drawback of having in machine learning low bias, is oftentimes it means that you have high variance, so that it generalizes extremely poorly to new data points that you actually haven't seen in the training, right? So for instance, with these very complex neural networks, you can pretty much fit every training data set perfectly, right? So that it really goes through every point here, so to speak, perfectly. But then if you now have new data points, right, you really overfit this method. And so it means that then on the new data points that you haven't seen during training, you typically perform quite poorly. And this is just to let you know that bias here, you know, is of course related to the notion of bias and fairness, but it's not quite the same, right? It speaks more to how well does the function that you learned, how well does it actually fit your training data? Okay, and now the big question is, okay, so now we know, you know, how, you know, supervised, you know, machine learning works, how we can use machine learning to classify things. So how, and we want, you know, we want to evaluate them, we want to know how good they are. So the question is, how do people typically measure whether a classifier is good for a particular application, right? And the go-to measure is accuracy, which is essentially the probability of correctly predicting the label. But this is not necessarily the best choice in some cases. So for instance, when you have unbalanced data, like for instance, traffic accidents on a particular intersection maybe happens once a year. So if your classifier just always tells you, no accident, you have a pretty high accuracy, right? Because the event is so rare. But of course, you actually want the classifier to be very good at predicting these really rare events, and so that in this particular case, having high accuracy is not enough to look at, right? And so because of this, and because of the oftentimes unbalanced nature of data sets, you can now construct additional classification criteria, like for instance, the true positive rate, which is the probability of your prediction saying 1 conditioned on the fact that it should be 1, right? So again, when it's positive, so when our target value is 1, that then your machine learning method actually predicts it also as 1. Whereas false positive rate is quite the dual, right? So if it's actually 0, so if you should predict it as a 0, and you actually still predict it as a 1, it's called the false positive rate, right? So in how many cases did you actually make a mistake by predicting by predicting it as a 1? And so depending on the use case, there are many different ways to measure how good a particular machine learning method works. A popular approach is also what's called a score function, or to use score functions, where you actually summarize essentially the input features, the input attributes that you have into a single value first. So you pose it as a regression problem. and then you use that value for the decision making. So that's, for instance, something that we've worked with quite a bit in our company. So we are working also with patient medical records, and specifically also patient medical records after they experienced a stroke. And there is what's called the FIM score, where depending on the features, the attributes of the patients, for instance, how well they can speak, how well they can move their hands and all this, there's a standardized set of tests. So you take all of these as features, and then you summarize the patient with a FIM score. And then the FIM score is used by medical practitioners to decide how to proceed with caregiving, for instance, physiotherapy, these types of things. And of course, very famously, a very simple score function is the body mass index, right? Which takes weight and height, combines it in some way, and then kind of based on the value, I should maybe lose some weight, it's unhealthy, or I'm fine, right? And of course, as we all know, also this is still pretty coarse-grained, right? So it doesn't apply, equally to everyone, and should be taken with a huge grain of salt, right? These numbers that you get there. Yeah, so that's something that is quite common also in practice, especially in the medical domain, is that you have these scores. And one way to actually turn a machine learning, also a classification-based machine learning model into a scoring model is by looking at what's called the conditional expectation. So here the idea is that we define the score as the expectation of our target variable given the particular feature configuration, so the expectation of the target variable. And this allows us also now to take a particular score function, for instance the BMI. We might also be interested in something like our target variable might be something like heart attack within the next 5 years. And then we can apply a threshold, right, on the BMI to make a particular binary decision of that a heart attack is happening within the next 5 years, I predict this or not. And so every threshold that you apply to the score function here is essentially a point on this green curve in this in what's called an ROC, so receiver operating characteristic curve, which every point on this curve essentially corresponds to one particular classifier that you can create based on the BMI, in this case here, based on the BMI score, right, by applying a particular threshold. And this contrasts here essentially the true positive rate and the false positive rate. And of course, what you want this green line to be like, ideally, is as high as possible immediately on the left, right? So you want the area under this curve to be extremely large, because that would mean that for a very small false positive rate, you can get a very high true positive rate, right? And that's exactly what you oftentimes are aiming for in for instance, clinical decision making. All right, now we might have, and this is where again fairness comes in here, we might actually have sensitive attributes. And features often, represent some characteristic of an individual that's considered sensitive, for instance, race, age, or gender. And in the rest of the talk, I'll typically use the letter A to refer to either one sensitive features or a set of sensitive features. And features are typically highly correlated, and that's a big problem. So it's not enough to just remove the sensitive feature itself, like for instance age, right? It's oftentimes possible to use the other features that are still there to build a very good predictor of that sensitive feature that you just removed, the sensitive attribute. And to kind of visualize this, on the left here, you have two groups, right? And a particular feature and the distribution of the values of that feature for these two groups. And you can see that, it's actually quite similar. The mean is a bit offset, right? But to just use that particular feature to distinguish group A and B is going to be tough, right? But now in machine learning, if you have many of those features and you actually aggregate them, and this is what you see on the right here, right? On the x-axis, you include in your machine learning model an increasing number of such features that have individually a pretty small discriminative power. But if you take them together, you're getting more and more towards perfectly predicting the sensitive feature that you actually wanted to conceal. And so this shows you that, yeah, again, removing sensitive features just because you don't want to include it is not a way to go in many cases. And then I should also mention that removing sensitive features can also cause harm, right? So it's not just about let's just forget about these features that we consider sensitive. Let's just throw them out and decorrelate everything else with them, and we are done. It could also cause harm because maybe the sensitive features are actually really important in making the decision, right? So for instance, age or gender in the medical domain, when we want to, for instance, predict what's the likelihood of a particular medication having a side effect. And so what this also kind of alludes to a bit right now is that, there is no one way or one easy way to cause a machine learning model to behave fair. It depends a lot on what we define as fair in the particular use case that we have, and how we actually enforce it in the data and in the model once we have agreed on what we want, in what way we want the machine learning model to be fair. And when you look at the literature over the last 10 years or so, three major fairness criteria have emerged there, and each expresses a property of the joint distribution between the sensitive attributes that you might care about, the target variable, and the classifier or score. Right? And yeah, these fairness criteria are called independence, separation, and sufficiency. And I'll just very briefly now go through them to give you a feel of of what these actually cause, or once you enforce them, how are they defined, and what type of fairness are they kind of enforcing? Right. So just to look at the the fairness criteria, the criteria on independence. So we say that a classifier satisfies independence if the probability. So I should say that in this case, just to make it easy, I looked again at a binary classification problem, right? So we have 1, -1, or 1, 0 as the possible outcomes. And so here we want that the probability of the classifier returning 1 conditioned on each of the groups is the same, right? So in other words, if we interpret R equals 1 as acceptance or give the treatment or whatever, independence is equivalent to the acceptance rate being the same for all groups selected by R, by A. And I think this is a pretty strong criterion, and it also can cause, of course, harmful side effects. For instance, if you maybe a certain subpopulation, the probability of a particular disease is actually lower, right? And now forcing these probabilities to be the same, of course, has an extremely harmful effect, right? You're predicting then with a higher probability that the disease is actually true, for instance, even though in this population you actually want these two probabilities here to be different, right? That's actually what you really want this machine learning model to return. Then there's this notion of separation. So a classifier satisfies separation if the false and negative and false positive rate for each group are the same, right? Or vice versa, the true negative and true positive rate. And what you can also prove actually mathematically, I won't go into the details here, is so the difference to the one before is that in addition to conditioning only on the group, so on the sensitive features, right, by setting A equals A here or A equals B, we are also conditioning on the on the target variable, right? So this is the difference here. Yeah, what I wanted to say is that, and this is, I think, quite interesting. So theoretically, you can actually show that oftentimes these criteria that I'm talking about right now can actually not hold at the same time, which again speaks to, right, there is not one way to make everything, for instance, make all of these criteria be satisfied. It's really a matter of choice. You kind of, before you train your model, before you collect the data, you have to, or you know, analyze the data, you have to make a choice which of these criteria do you actually want to hold, right, for your particular use case that you care about. And then there are another criteria called, you know, sufficiency and calibration. Again, I don't think it makes a lot of sense to go into the details here, but this is kind of just to give you an idea of, you know, there are, depending on the application domain, certain criteria that you want to be true, but you really have to think hard about which ones are those, and you have to choose. You cannot have your cake and eat it as well, right? So you really have to choose between these criteria, and if you choose one, you are likely violating another one, right? And so this is kind of also maybe a good take-home message, is that there is no magic bullet also for you know, reducing or mitigating biases in machine learning methods. It's an active choice that you have to make, and you really have to understand what of the choices you need for your application. And then finally, just to briefly mention this, there are different ways to satisfy fairness criteria, and this is really a big area of research at the moment. But you can, for instance, pre-process the data. For instance, you're removing training data, you're adjusting the feature space in a way that no matter what you then train on it, you're satisfying your criteria that you care about. You can kind of incorporate the constraints, so these you know, fairness criteria as constraints in your optimization process. That's something that people like to do and have investigated a lot in the machine learning domain, so that you can guarantee that you know, once the model is trained, it behaves according to the criteria that you care about. And then there's also post-processing, which means essentially looking at the classifier after training, so post hoc, and making sure that by changing the model in certain ways, that it satisfies the criteria. Lastly, I should say that you know, these criteria that I mentioned here, and there are a couple of others, you can imagine, you know, lots of them have been now kind of invented and tried and included in them in machine learning applications. All of these criteria that I mentioned here are actually observational, meaning that they specify some property of this joint distribution between A, Y, and R. But you know, as probably many of you know, the same causal mechanism, right, that underlies the, you know, the data generating process, right, can lead to the same observational data. So different causal mechanisms can lead to the same observational data. And since the criteria are operating on the observational data, they cannot distinguish situations, right? So if a different causal mechanism leads to the same observational data, these fairness criteria will not be able to distinguish that. And that can cause also certain problems. And that's also why you see a pretty large overlap between the fairness in machine learning community and the causality community. And this is just something that I wanted to hint. And so in some cases, if you have, you know, very strict kind of conditions on how you want your machine learning methods to operate and to make decisions, or to help in making decisions, you might actually need to go to use more powerful tools, like, for instance, causality. Okay, so this was the part about fairness in machine learning, which kind of was supposed to provide a bit of an overview of, you know, the types of things that people have worked on in this area, and you know, what is kind of the state of the art there. Of course, this was an extremely high level presentation. Now I'm going to use you know, roughly, you know, 20 minutes or so to talk a little bit about explaining the behavior of machine learning models, which is also something that, you know, my group is working on, is working on quite actively. Right, and so you know, explainable AI is a, and many of you probably know this, is a pretty you know, hot research topic. There are hundreds of methods proposed, LIME, SHAP, many others. I would say almost every week there's probably a new paper or a bunch of new papers on a new method for explainable AI. It has also come quite a bit under scrutiny because, you know, a lot of people are kind of going and, you know, oh yeah, you know, explainable AI is really important, and everyone agrees on that. But then again, it goes kind of back to what I said before. You know, what is it actually that you want to achieve by explaining something, right? And depending on what you want to achieve, you know, your methods must be very different and must satisfy different constraints, right? And so the first couple of years in explainable AI was a lot about, you know, taking images, for instance, and somehow, you know, visualizing, you know, where, so intuitively speaking, right, where the machine learning, the deep learning model was actually looking at when it was making a decision that that's a bird, right? So which parts of the image was the machine learning method paying attention to, which part of the input feature space when it made the decision, right? And then people argued, oh yeah, this looks reasonable, right? So I can see that it looks at the beak and the eye of the bird. So I think it explains pretty well, you know, that must be a bird, right? And of course, this is very informal, and a lot of work has been done in this area. And then there was a wave of really pretty harsh criticism of, we have to change this, we have to be more goal-oriented and really define more rigorously, you know, what is it actually that we want to achieve with explainable AI. And so, you know, just to mention to you, it's a big and exciting area. I think very good to also to get into as a new researcher. But it's also important to understand what are, you know, the existing criticisms of this, and what you know, what are the current trends in, you know, and what are the particular more well-defined problems that people are now picking to use explainable AI for. And in our group here at NEC, we are currently focusing on the following questions, and this is what the rest of my talk is going to touch on briefly. So given data model and a specific prediction, right, what are the data points that influenced said decision? And this is really a kind of a counterfactual question that we're asking here. We're asking, how would the model behave if this particular data point or this particular set of data points wasn't actually part of the training data? And then you could use that. So once you have a method that tells you or allows you to answer these counterfactual questions, so how would the model behave if something were not part of the training data? Then you can also relate this again to the concept of fairness and to the criteria that I mentioned, because you can check, right, the machine learning model that I have right now and this particular prediction that it's making, or the set of predictions that it's making. To what extent does it satisfy a particular criterion that I might care about? And how can I actually change the data set, right? Remove data points, downweight data points, such that it satisfies the constraints that I care about, right? So this goes a bit in the direction of, it's a combination of pre-processing, but also changing the model itself to allow, to adapt to particular criteria of fairness that we might care about. And just very briefly, my group is working a lot on graph neural networks. I mentioned this before. There are lots of, you know, applications in this area, from chemical compounds to patient graphs to biomedical knowledge graphs. And I wanted to very briefly mention a particular application that we have worked on, where we also have developed an explainable AI method that then also would allow us to address you know, questions like fairness and bias in decision making. And this is about what's called polypharmacy side effect prediction. So the idea here is that a lot of people are prescribed more than one drug. Drugs can have side effects, but they can also have side effects that only occur when you take drugs together, right? And so the kind of the combinatorial search space of what kind of drugs can you take together is huge. So what you kind of want to try to do in polypharmacy side effect prediction is you want to predict, you know, which of the drugs when you take them together at the same time, and again, this happens a lot, especially in elderly patients, can lead to unintended side effects. And what we do here is we essentially have a knowledge graph that consists of proteins and drugs, and the proteins have particular interactions with each other that are potentially known from the literature. We also know that particular drugs interact, so for instance, upregulate or downregulate certain proteins. So what we do is we just build this really big, what we call knowledge graph of drugs and proteins and how they interact with each other. And then we also have already, for some of the drugs, we know when you take them together, they do have a particular bad side effect, right? Like for instance, migraine or something like this. And so now you can pose the problem of predicting whether two drugs actually have a side effect when they're taken together as the problem of predicting missing links, right, of a particular type in this knowledge graph. And so, knowledge graph, I mentioned this, consists of what we call triples. It's typically consisting of a subject, a relation, and an object. So something like, in this case, it's a space needle located in Seattle, right? Or drug A upregulates protein B in our biomedical knowledge graph. And our training set is a set of known triples. So we have this knowledge graph, which we know. It's kind of, you can think of it as a particular data set. We might also have that, by the way, that in the biomedical use case, we also have patients in there and their attributes. So this is where the fairness and the concept of fairness comes in, and the concept of sensitive features. And then we essentially predict new relations using machine learning, right? And this is kind of neural network based, typically what people do there. So the big question is, how can we make the predictions of these, for instance, polypharmacy side effect prediction methods that are also oftentimes personalized, so tailored to a particular person? How can we make them more explainable to understand, why does the model actually think that, these two drugs taken together by that particular patient could actually cause a side effect, right? And we want our explanations to be faithful. What this means is that we wanted these explanations to represent the reasoning process of the model, right? So we want to understand, how did the model, starting from the features, come to the particular conclusion mechanistically, and that should be explained by our method that we are using here. And so we have designed a technology that we call gradient rollback. The idea here is that we want to generate faithful explanations. We also, again, as I said in the beginning, we do this by identifying training instances that have influenced the prediction that we're currently looking at, so that we can then mitigate, for instance, bias or other types of problems. And we want to apply this to this particular type of problem setting of knowledge graph embeddings. So what we essentially did, I want to cut it short here because we are running a little bit out of time, is that what we do essentially is, while we are training this model, we are keeping track of the changes of the parameters that every update of stochastic gradient descent, which is an algorithm typically used to train neural networks, kind of causes in the parameters. So we keep track of all of these changes. And that's why it's called gradient rollback, we can actually, by tracking the influence, right, over time, so this is a particular update step from stochastic gradient descent. This is, the aggregated influence of a particular training triple D prime at a particular time. And then we kind of, again, you have to imagine it as we're kind of keeping track for every data point, for every input, we're keeping track of how did it actually change the parameters of the model. And when we keep track and record all of these changes, after we have finished training, we can then, so to speak, roll back. So we can take back the influence that particular features and data points had on the weights on the parameters of our machine learning model. And then we can say, well, and then we can use this to answer these counterfactual questions that I mentioned before. So, for instance, were this data point not part of the training data, how would our model actually behave? Or where this particular feature or the sets of features not part of the training data, how would our model behave? And by answering these counterfactual questions, we can then also analyze, the biases and mitigate also the biases that we have in the model and in the training data itself. Yeah, and then use this, of course, also to explain the predictions of the machine learning model. So because I wanted to also leave at least 10 to 15 minutes for questions, again, I want to call it a bit short. We also have make it a bit short here. We also have theoretical results where we can show that when we answer these counterfactual questions about the machine learning model that we have, so when we answer something like, how would the model behave, were we to remove a particular training instance, we can also, and this is really nice, I think, we can also show mathematically, so we can prove that the mistake that we make when we answer these, so the approximation error that we make when we answer these counterfactual questions, that this can be bounded in a particular way. So we have also a guarantee that these questions can be answered in a pretty accurate way, and we can rely on them also in a pretty stable way. And then I just very briefly wanted to mention that we also evaluated this and we compared to other types of methods for explaining machine learning methods, and we did quite well. There's also code available. Again, I'm happy to share the slides, and you'll also have it on the video. So if you want to kind of learn more about this particular line of research and also want to experiment with the code that we have, you can do this. You can also reach out to me, of course, if you're interested. I finally wanted to mention that, and this is something that, actually I had in my conversation before this presentation, I had also with others in the room, was that I think that, to evaluate how well explainable AI works, you really have to use also and look at the system and how it interacts with the human decision maker, right? And so that's something that we are currently working on, is we are really integrating these explainable AI methods that we are developing in user interfaces. And we really observe and do user studies to test, for instance, how does the efficiency change of the users interacting with the system over time, right? Are the decisions that the human makes based on the machine learning method, does that actually get more or less biased, for instance, with respect to the fairness criteria that I mentioned before, right? Because you might make your machine learning model satisfy these fairness criteria, but then when you actually put a human in the loop, right, and the human is using your method for predictions and is then basing their decision making on the predictions of the machine learning model, the user who makes the decision in the end might actually be more biased than without the machine learning method, right? And so I think this is really crucial in this line of research, is to go a bit away from kind of the, just kind of analyzing kind of theoretical properties only and kind of defining some measure of goodness and then satisfying it or trying to be better than another method, but to also really look at the system that involves the human and the AI system as one, and to analyze that as one system, right? And to see how does the decision making of the human change. And with that, because I think that's quite important as a take-home message, I'll finish my presentation. And again, if you have, I went pretty quickly over the last part of our research, which is pretty specific. If you have more questions about it, also feel free to contact me, and I can talk more about it. And so, yeah, thank you very much for your attention. Thanks.